Hi everybody, in this lesson today we're going to look at something called anti-differentiation, which says that if we've given a function and we find the derivative and then we use the idea that integration is the reverse process to differentiation to help us actually find an integral. And so there are four key ways in which we can use this idea. Firstly, if we're looking for the derivative itself to be integrated. The second way is if the derivative with an extra constant is being integrated. The third way is if one term of the derivative is being integrated. And then the final way is the derivative with extra terms. Is being integrated. So these are the four ways. And what we're going to do is we're going to look at each of these ways in turn. Now this is something that comes up in every exam or lots of exams, especially now that the new courses come in and we can integrate in less ways. So in every situation though, the first step is exactly the same. We write down that the derivative of, or the integral of the derivative is equal to the original function that we had plus c. Now, we have four examples, and that's to go through the four different situations that we can come across. So, first one, we're given a function, we're asked to find the derivative, and hence find an integral from that. So, let's start. So, f of x is e to the x take 1 on x. So then the derivative, f dash of x, well, it's just going to be the exponential to that function. So, e to the x take 1 on x, and then times by the derivative of the power, which is the derivative of x take 1 is just 1, times by the bottom function, minus the top function, multiplied by the derivative of the bottom function, all over the bottom function squared. And so we get that as our derivative. So it's e to the x take 1 on x, multiplied by, now that's x take x plus 1, all over x squared. So your x take x just gives you 0. So you get e to the power of x take 1 on x times by 1 on x squared, which is just e to the power of x take 1 on x all over x squared. Okay, so that's our derivative. Now we know our first step, so we can say, write down our first step, that the integral of this derivative, e to the x take 1 on x all over x squared dx, is equal to the original function. Let's just remind ourselves what it was. So it was this exponential to the power of x take 1 on x plus c. Now, we don't quite have what we're looking for. We're close, but we've got a different power of e. Okay, but there must be a link between what we're doing here and that power. So if you stare at that power closely, well, I can write that as x on x take 1 on x. And that's going to give me what I want. Because you see, if I then simplify that, so just writing that down, I can then say that it's x on x is just 1, so it's e to the power of 1 take 1 on x squared dx is e to the power of x take 1 on x plus c. And so that's my final answer. Now you might say, well, with this e, do I need to change the power there to 1 take 1 on x? It's really unimportant. All we're looking for is the answer of this integral here. So we needed to make the change here because that was what we were given in the original question. But whether we change it on the right-hand side or not is not going to matter. it's still going to be the same thing, so it's still going to be the correct answer. Okay, now in this case, we're given f of x equals ln x squared take 3 plus ln x greater than root 3. So sometimes you won't be given the modulus, but sometimes what will be done instead is that the correct domain is given, so there's no need for the modulus. So any numbers equal to root 3 or lower will make this function undefined, but we've cut all those values out. Okay, so f of x is ln x squared take 3 plus ln x, and we know how to differentiate that. So f dash of x is 2x on x squared take 3 plus 1 on x. Now, please do not go and do something, it's easy to do something a little bit, I guess, misguided here, and it's easy to think you're in the habit of integrating, so we've got to add c, but we're differentiating. So keep in your mind absolutely clear, where am I differentiating, where am I integrating? And when you differentiate, don't put a plus c there. Okay, so the derivative is equal to that, but that doesn't really help us integrate this yet, so let's put it all over the same denominator. So here, 2x over x squared take 3, where I can times that by x on x, and here I've got 1 on x, so I can times that by x squared take 3 on x squared take 3. Okay, so here I'm going to get 2x squared, and then it's going to be plus x squared take 3 all over x by x squared take 3. So that's going to give me 3x squared take 3 all over x cubed take 3x. Now if we look at that closely and look back to our original function, we've already got the denominator. Okay, we've already got x squared take 3x. But we now, need this 1 take x squared bit on the top. Now I don't quite have that yet, so if I come up to this line here, then what I can do is I can take out a common factor of minus 3. So if I take out a common factor of minus 3, I get minus x squared plus 1 all over x cubed take 3x. And then just putting that around the other way, it'll be minus 3, 1 take x squared all over x cubed take 3x. So now I'm ready to do my integral. So let's write down the integral of the derivative equals the original function. So there's minus 3, 1 take x squared over x cubed take 3x dx is equal to ln x squared take 3 plus ln x plus c. And we've got the exact integral we need apart from this minus 3. So I'm going to bring the minus 3 out. So it's going to be minus 3 integral of 1 take x squared on x cubed take 3x dx is equal to ln x squared take 3 plus ln x plus c. And then divide this minus 3 by on the other side. So we're going to get 1 take x squared, integral of 1 take x squared, x cubed take 3x dx is equal to minus 1/3 ln x squared take 3 take 1/3 ln x plus c. And there's our final answer for this one. So all we had to do in this case was just take out that constant and move it to the other side. Okay, in our third example, we've got f of x equals sine x, or rather 2x plus 5 sine pi x. Okay, so my derivative, well, we're going to use the product rule here. So it's the derivative of 2x plus 5, which is just 2 times sine x plus the first function, which is 2x plus 5, times by the derivative of sine pi x, which is cos pi x, times by pi. So now I can just write down that this equals the original function. So the integral of 2 sine pi x plus 2x plus 5 pi cos pi x dx is equal to 2x plus 5 sine pi x, and we need that plus c. Okay, alright, but I know how to do this integral without actually needing to use any fancy tricks. So I can break it up into 2 sine pi x dx plus pi. Well, I'm going to bring the pi out to the front, so because it's just a constant. So we learned last time in the last example that we could do that, and that will just leave me with 2x plus 5 cos pi x. And this is the integral we're looking for. So we're almost there, really. So then it's just going to be 2x plus 5 sine pi x plus c. Now I need to just complete this integral here. So the integral of 2 sine pi x is just negative 2 cos pi x. And I need to, without the dx, and I also need to go through and divide by pi. And then it's going to be plus pi 2x plus 5 cos pi x is equal to 2x plus 5 sine pi x plus c. So it gets a bit more complicated, but if I bring this to the other side, I'm just going to add it, and then I'm going to divide everything through by pi. So the integral of 2x plus 5 cos pi x is equal to 2x plus 5 sine pi x, and that will be plus 2 on pi cos pi x plus c, but I also said I was going through and dividing everything by pi, so this will be all over pi, that'll be all over pi squared, and it'll have no effect on our c. C is so arbitrary that we don't even need to change it when we divide or add things to it. Okay, potentially here we should also add in plus c1 plus just because I'm integrating that, so I should remember my c in there. It'll get absorbed into this arbitrary constant c here, but just for completeness I should add it in there. Okay, and so now with this function we have negative out the front of 2 ln x plus 1 all over 4x squared. So I'm going to have to find the derivative, so f dash x. Now I'm just going to leave that negative out the front, and then it's going to be the derivative of 2 ln x plus 1, so the derivative of 2 on x times by the bottom function, so times by 4x squared, all over, or before we do all over, then it's going to be take 2 ln x plus 1, and then times by the derivative of the bottom, which is 8x, and now that's going to be all over 16x to the 4. Now this negative sits out the front of everything, so I'll just put it down on that line, out the front. So now I can cancel the squared and the x, and that's going to give me a negative out the front of 8x, take 2 ln x plus 1, 8x, all over 16x to the power of 4. So then it's going to be negative 8x, 1 take. Now we'll expand this out, so it's a negative by out the front, so it'll be negative 2x, 2 ln x rather, take 1, all over 16x to the power of 4. So we cancel down the 4 to a 3, and the x to a 1, and then cancel the 8 and the 16 to a 1 and a 2. And this is also going to be 1 take 1, so that's all going to cancel, and we're going to get negative out the front of negative 2 ln x over x cubed, and then the double negative will just cancel to make a positive, so we get 2 ln x on x cubed, or rather 2x cubed, and then the 2's cancel to give us ln x on x cubed. So we can say, our first line will say that the integral of ln x on x cubed is equal to this horrible function back here, which was minus 2 ln x plus 1 on x to the 4 plus c. Okay, so now I need to do my function, but it's not entirely obvious how to do it. But what I can do is, if I look closely here, if I split that up into ln e to the 2x take 1 plus ln x, then I can split that into two different terms, one of which will be ln x on x cubed. So I can then write down the integral of ln e to the 2x take 1 plus ln x all over x cubed, which is equal to the integral, well, ln and e just cancel, so that'll just be 2x take 1 on x cubed plus the integral of ln x on x cubed. Now, I know how to do this one. We've already done that. So I just need to focus on this now. Is there a way I can do this? Well, let's look at it closely. Integral of 2x. If I split that up into 2x on x cubed, I'll just get a constant times x to some power. I know how to do that one. Take 1 on x cubed. That's again, that'll just be x to some power, and I know how to do that. Plus the integral of ln x on x cubed dx, and I know how to do that one as well. So if I cancel the x and the cube to a squared, I'll get the integral of 2x to the minus 2, take x to the minus 3 dx, plus the integral of ln x on x cubed dx. Okay, so adding 1 then dividing by the new power. So I add 1 here, that'll give me x to the minus 1. I'll have a 2 out the front, divide by minus 1. Then it will be take x to the minus 2, divide by minus 2, plus c, and then it will be plus the integral of ln x on x cubed dx, which is then just minus 2 on x, and then it will be plus 1 on 2x squared, plus c, plus, now I'm ready for my integral, and it's take, it'll be take 2, and I should write that here, so take 2 ln x plus 1, where the plus 1 is outside the ln x, on x to the power of 4, and that will be plus c. Okay, so to finalize that, I can just write it as 1 on 2x squared, take 2 on x, take 2 ln x plus 1 on x to the power of 4, plus c, so that both the c's can just get absorbed in one c, and that's my final answer to this integral.